Hi, my name is Giacomo, and today I'm going to show you a RAG application which I've built. RAG is called RAG. It's an acronym for Retrieval Augmented Generation. The generation is well, because we're using a large language model on artificial intelligence to generate text or content. Retrieval Augmented Generation is different from normal AI generation because we provide context to the large language model, which it will not have, because the information which we have is personal and is not a part of the training data of this large language model. And how do we do this? Well, here's a very simple kind of scheme of how it works. We take a document, which is ours personal, and we divide it into chunks. Why do we do this? Well, once we ask a question and we have pieces of information, we need to find the most relevant pieces of information to then send to the large language model as context. As we cannot semantically compare these, because this will not be very accurate, we need to find some other way to approximate which chunks or which pieces of text are more relevant to our question. And we do this by embedding or vectorizing. What this basically does is it locates, or it puts each chunk of text. For example, here I'm using an essay and I've divided it into chunks of 100 words. It takes this essay, divides it into chunks, and then embeds them. Embedding basically means that it puts each of these texts in a place in a multidimensional space, where each dimension represents some quality or some characteristic of this text. And what this will basically do is allow us to compare which piece of text is mathematically closer to our question. We do this by something called cosine similarity. Basically, we also, once we receive the question, we also embed it, we also vectorize it, and this also collocates it in 3D space, multidimensional space. Here I'm using 768 dimensions. And once this is done, we can look at which chunks of text are closer to this question by looking at the angle from the origin to the place in this multidimensional space. This vectorization it has nothing really concrete. It's just a bunch of numbers, as you can see here. This is one of the chunks vectorized. It's just 750 numbers, which give the position in space for each dimension in this space. So yeah, once we have these chunks and we put them in a database, we can then basically run queries through our app. So also vectorize these queries and find the pieces of text, these chunks, that are more relevant to our question. And then we simply feed these, as you can see here, into our language model. We feed the chunks that are most relevant and the question, and basically ask it to answer our question just using these chunks. So I can show you how this actually works in an app. I just very quickly built an app. So I can ask a question which is relevant to this essay. This is a Camus essay. So I will ask a question about Camus, and it will try to answer it with the relevant chunks that has been given. So now it's vectorizing this question that I've sent and comparing it to my vector database, which is just the whole essay, 70 pages, being already vectorized before. We can also check here. It has returned the top 3, because I've just chosen to return the top 3 most relevant pieces of text, chunks, to my question. Then it has sent these relevant chunks in the question to a large language model, which is local on my computer. This is basically so that no data is sent to an external server, so that it's just more secure. And yeah, this is just an answer given based off simply the context that I have provided to a large language model, which is obviously really, really good if you have personal documents, for example, and maybe they are very large, and you want to query a large language model on these personal documents. You can do this through a simple RAG pipeline. This is one pipeline, which is basically one document or a bunch of documents, and then you just submit one query and do a similarity search through all of these documents. Another application which I've found is very useful is this email generator. I spoke with Ms. Casagrande, and she asked me if I could create an app which found at which times which students were free in a day, and then prepared an email to send to them with the times inside. So this works very similarly, but the chunks now are just rows of a CSV file, of an Excel file, let's say. And the way I use RAG is I provide context on the structure of this file, which is just a timetable from ManageBack. And I also provide context on my question. So I just give my question. And I ask a large language model to convert this question into an executable code in a language which is made for database retrieval. And then here, I simply run the code that it gives me in order to retrieve the data that I need. So it's basically converting text which I've sent to code which can answer my question through my data. Then, once it actually finds the data that I have, that I needed, I submit this, which is basically the free times in that day, with the email which it has found, and with the name of the student which it has found. I submit all of this to a large language model once again to create the email ready to send. So this is just an example. If there is more than one student with the same surname, it will ask you which of the two students. And then once I generate the email, it will send all of this information to the language model, and this will generate an email with the correct free times on that day. This takes a while, of course, because it's local, but as you can see, these are the availabilities of that student on that day. And this is a ready-made email, and here's the email of the student, so that, basically it's super quick and easy to do for the teachers. Otherwise, you would have to search through which subjects the person is taking, and then compare this to the timetable, and then see at which times these subjects are not taught on a particular day. This is just very quick and automated, basically. Of course, there are some issues with RAG done this way. This is very simplistic RAG pipeline. One thing we could do is agentic search or agentic behavior. We could combine more pipelines, so create more RAG pipelines with different types of documents, and then have some context be either made by a large language model or make it ourselves regarding what each of these pipelines or tools can actually do, or what information it has. So then I can basically take my query, send it to a large language model along with the context of all of my agents, which are kind of these, and then I'll say, look, you should use this, and this. The large language model will suggest which agents to actually use, maybe 2 or 3, we can choose how many. And then we can run the similarity search in the RAG pipelines for these selected agents. This, first of all, gives us more context from more, from more pipelines, so more data. But also, it makes us able to answer a larger variety of questions and more accurately with the same application, within the same application. So I will not have to change between different interfaces as I've just done, because the large language model will be able to query different agents. Another thing we can do, and an issue I've found is, for example, with the Camus question, it's a very broad question. And sometimes, because of this very vague question, the context that I will receive will be not very specific. So what we can do is actually generate questions from this initial query. So basically subdivide the initial query into more queries. And then we can query our pipeline on these individual questions and then send the answers to this query with the initial question back to the large language model. So it has more context regarding our question. And this has been shown to be very, very effective. Of course, all of these further steps will decrease the speed of the application, especially if it's local, as in this case, but it will increase the accuracy. Also, what we could do is check if the context which we have been provided is actually relevant to our question. Sometimes, especially for longer chunk sizes, for example, 100 is a really long chunk size, the context of the middle of the chunk is kind of lost. It's not really understood well by the embedding model. What this kind of means is that sometimes either the text that has been retrieved is not relevant, or the pieces that have been retrieved that are actually relevant are kind of lost. We can simply send the retrieved text with the initial question to a large language model to ask it if or if not the retrieved chunks are relevant. And if they are not, we can rerun the similarity search to see if we all have different results.